When the fuel air charge starts to burn, the compression rate. When the fuel air charge starts to burn before the spark plug fires. Detonation occurs when the fuel air charge is ignited by the spark plug. But instead of burning at a controlled rate, it explodes, causing cylinder temperatures and pressures to spike very quickly. If this condition exists for very long, the engine can be damaged or destroyed. One of the reasons for using engines with high compression ratios is to obtain long-range fuel economy, to convert more heat energy into useful work than is done in engines of low compression ratio. Since more heat of the charge is converted into useful work, less heat is absorbed by the cylinder walls. This factor promotes cooler engine operation, which in turn increases the thermal efficiency. Here again, a compromise is needed between the demand for fuel economy and the demand for maximum horsepower without detonation. Some manufacturers of high compression engines suppress detonation at high manifold pressures by using high octane fuel and limiting maximum manifold pressure. Indicated horsepower. The indicated horsepower produced by an engine is the horsepower calculated from the indicated mean effective pressure and the other factors which affect the power output of an engine. Indicated horsepower is the power developed in the combustion chambers without reference to friction losses within the engine. This horsepower is calculated as a function of the actual cylinder pressure recorded during engine operation. To facilitate the indicated horsepower calculations, a mechanical indicating device, such as is attached to the engine cylinder, describes the actual pressure existing in the cylinder during the complete operating cycle. This pressure variation can be represented by the kind of graph shown in Figure 1-39. Notice that the cylinder pressure rises on the compression stroke, reaches a peak after top center, and decreases as the piston moves down on the power stroke. Since the cylinder pressure varies during the operating cycle, an average pressure, line AB, is computed. This average pressure, if applied steadily during the time of the power stroke, would do the same amount of work as the varying pressure during the same period. This average pressure is known as indicated mean effective pressure, and is included in the indicated horsepower calculation with other engine specifications. If the characteristics and the indicated mean effective pressure of an engine are known, it is possible to calculate the indicated horsepower rating. The indicated horsepower for a 4-stroke cycle engine can be calculated from the following formula, in which the letter symbols in the numerator are arranged to spell the word Planck. To assist in memorizing the formula, indicated horsepower equals Planck 33,000, where P equals indicated mean effective pressure. In psi L equals length of the stroke. In feet or in fractions of a foot, A equals area of the piston head or cross-sectional area of the cylinder. In square inches, N equals number of power strokes per minute, RPM 2. K equals number of cylinders. In the formula above, the area of the piston multiplied by the indicated mean effective pressure gives the force acting on the piston in pounds. This force multiplied by the length of the stroke in feet gives the work performed in 1 power stroke, which, multiplied by the number of power strokes per minute, gives the number of foot-pounds per minute of work produced by 1 cylinder. Multiplying this result by the number of cylinders in the engine gives the amount of work performed in foot-pounds. Compression power exhaust intake, peak pressure. Pressure in cylinder. P. A. B. Indicated mean effective pressure. Imp. Spark. DC. E. I. Bottom center top center BC. Figure 1-39. Compression ratio. 1-31. By the engine. Since HP is defined as work done at the rate of 33,000 foot-pounds per minute, the total number of foot-pounds of work performed by the engine is divided by 33,000 to find the indicated horsepower. Example. Given. Indicated mean effective pressure. P equals 1.65 pounds/into. Stroke. L equals 6 in or 0.5 foot bore equals 0.5 in RPM equals 3000 of cylinders. K equals 12. Indicated HP equals Planck 33,000 foot-pounds/min. Find indicated HP. A is found by using the equation A equals 1/4 pi d2. A equals 1/4 times 3.1416 times 5.5 in times 5.5 in equals 23.76 in 2. N is found by multiplying the RPM by 1/2. N equals 1/2 times 3000 equals 1500 RPM. Now, substituting in the formula, indicated HP equals 1.65 pounds/in 2 times 0.5 in times 23.76 in 2 times 1500 RPM times 33,000 foot-pounds/min. Indicated HP equals 1069.20. Brake horsepower. The indicated horsepower calculation discussed in the preceding paragraph is the theoretical power of a frictionless engine. The total horsepower lost in overcoming friction must be subtracted from the indicated horsepower to arrive at the actual horsepower delivered to the propeller. The power delivered to the propeller for useful work is known as brake horsepower, bhp. The difference between indicated and brake horsepower is known as friction horsepower, which is the horsepower required to overcome mechanical losses, such as the pumping action of the pistons, the friction of the pistons, and the friction of all other moving parts. The measurement of an engine's bhp involves the measurement of a quantity known as torque or twisting moment. Torque is the product of a force and the distance of the force from the axis about which it acts. Or, torque equals force times distance, at right angles to the force. Torque is a measure of load. and is properly expressed in pound-inches, pounds-in, or pound-feet, pounds-foot. Torque should not be confused with work, which is expressed in inch-pounds, in pounds, or foot-pounds, foot-pounds. There are numerous devices for measuring torque, such as a dynamometer or a torque meter. One very simple type of device that can be used to demonstrate torque calculations is the Prony Brake. Figure 1-40. All of these torque measuring devices are usable to calculate power output of an engine on a test stand. It consists essentially of a hinged collar, or brake, which can be clamped to a drum splint to the propeller shaft. The collar and drum form a friction brake, which can be adjusted by a wheel. An arm of a known length is rigidly attached to, or is a part of the hinged collar and terminates at a point that rests on a set of scales. As the propeller shaft rotates, it tends to carry the hinged collar of the brake with it and is prevented from doing so only by the arm that rests on the scale. The scale indicates the force necessary to arrest the motion of the arm. If the resulting force registered on the scale is multiplied by the length of the arm, the resulting product is the torque exerted by the rotating shaft. For example, if the scale registers 200 pounds and the length of the arm is 3.18 feet, the torque exerted by the shaft is 200 pounds times 3.18 foot equals 636 pounds-foot. Once the torque is known, the work done per revolution of the propeller shaft can be computed without difficulty by the equation. Work per revolution equals 2 pi times torque. If work per revolution is multiplied by the RPM, the result is work per minute, or power. If the work is expressed in foot-pounds per minute, this quantity is divided by 33,000. The result is the brake horsepower of the shaft. Power equals work per revolution times RPM and bhp equals work per revolution times RPM 33,000. 2 pi r times force on the scales. Pounds times length of arm. Foot times RPM 33,000. 1-32. Scale 200 pounds. 0. Friction adjusting wheel. 300,100. Collar. Arm hinge. 200. Drum. Propeller shaft. Length of arm 3.18 foot. Figure 1-40. Typical Prony brake. Example. Given. Force on scales equals 200 pounds. Length of arm equals 3.18 foot. RPM equals 3,000. Pi equals 3.1416. Find bhp substituting in equation. bhp equals 6.2832 times 200 times 3.18 times 3,000. 33,000. Equals 363.2. Equals 363. As long as the friction between the brake collar and propeller shaft drum is great enough to impose an appreciable load on the engine, but is not great enough to stop the engine, it is not necessary to know the amount of friction between the collar and drum to compute the bhp. If there were no load imposed, there would be no torque to measure, and the engine would run away if the imposed load is so great that the engine stalls. There may be considerable torque to measure, but there is no RPM. In either case, it is impossible to measure the bhp of the engine. However, if a reasonable amount of friction exists between the brake drum and the collar and the load is then increased, the tendency of the propeller shaft to carry the collar and arm about with it becomes greater, thus imposing a greater force upon the scales. As long as the torque increase is proportional to the RPM decrease, the horsepower delivered at the shaft remains unchanged. This can be seen from the equation in which 2 pi r and 33,000 are constants and torque and RPM are variables. If the change in RPM is inversely proportional to the change in torque, their product remains unchanged, and bhp remains unchanged. This is important. It shows that horsepower is the function of both torque and RPM, and can be changed by changing either torque, RPM, or both. Friction horsepower. Friction horsepower is the indicated horsepower minus brake horsepower. It is the horsepower used by an engine in overcoming the friction of moving parts, drawing in fuel, expelling exhaust, driving oil and fuel pumps, and other engine accessories. On modern aircraft engines, this power loss through friction may be as high as 10 to 15% of the indicated horsepower. Friction and brake mean effective pressures. The indicated mean effective pressure, IMP, discussed previously, is the average pressure produced in the combustion chamber during the operating cycle, and is an expression of the theoretical, frictionless power known as indicated horsepower. In addition to completely disregarding power loss to friction, indicated horsepower gives no indication of how much actual power is delivered to the 1-33. Power stroke, FMEP, BMEP, IMP, FHP, Figure 1-41. Power and pressure. Propeller shaft for doing useful work. However, it is related to actual pressures that occur in the cylinder, and can be used as a measure of these pressures. To compute the friction loss and net power output, the indicated horsepower of a cylinder may be thought of as two separate powers, each producing a different effect. The first power overcomes internal friction, and the horsepower thus consumed is known as friction horsepower. The second power, known as brake horsepower, produces useful work at the propeller. That portion of IMP that produces brake horsepower is called brake mean effective pressure, BMEP. The remaining pressure used to overcome internal friction is called friction mean effective pressure, FMEP. Figure 1-41. IMP is a useful expression of total cylinder power output, but is not a real physical quantity. Likewise, FMEP and BMEP are theoretical but useful expressions of friction losses and net power output, although BMEP and FMEP have no real existence in the cylinder. They provide a convenient means of representing pressure limits or rating engine performance throughout its entire operating range. There is an operating relationship between IMP, BMEP, and FMEP. One of the basic limitations placed on engine operation is the pressure developed in the cylinder during combustion. In the discussion of compression ratios and indicated mean effective pressure, it was found that, within limits, increased pressure resulted in increased power. It was also noted that if the cylinder pressure were not controlled within close limits, it would impose dangerous internal loads that might result in engine failure. Therefore, it is important to have a means of determining these cylinder pressures as a protective measure, and for efficient application of power. If the BHP is known, the BMEP can be computed by means of the following equation. BMEP equals BHP times 33,000 length given, BHP equals 1,000. Stroke equals 6 in bore equals 5.5 in RPM equals 3,000. Number of cycles equals 12. Find BMEP. Find length of stroke in foot. L equals 6 in equals 0.5 foot. Find area of cylinder bore. A equals 1/4 pi O2. A equals 1/4 times 3.1416 times 5.5 in times 5.5 in A equals 23.76 in 2. Find number of power strokes per min. N equals 1/2 times RPM. N equals 1/2 times 3,000 RPM. N equals 1,500. Actual pressure. IMP. TCBC. Friction. Accessories BHP. Impeller. 1-34. Then, substituting in the equation, BMEP equals 1,000 BHP times 33,000 foot-pounds slash min 0.5 foot times 23.76 and 2 times 1,500 strokes slash min times 12 equals 154.32 pounds slash in 2. Thrust horsepower. Thrust horsepower can be considered the result of the engine and the propeller working together. If a propeller could be designed to be 100% efficient, the thrust and the BPH would be the same. However, the efficiency of the propeller varies with the engine speed, attitude, altitude, temperature, and airspeed. Thus, the ratio of the thrust horsepower and the BHP delivered to the propeller shaft will never be equal. For example, if an engine develops 1000 BHP, and it is used with a propeller having 85% efficiency, the thrust horsepower of that engine-propeller combination is 85% of 1000, or 850 thrust HP. Of the 4 types of horsepower discussed, it is the thrust horsepower that determines the performance of the engine-propeller combination. Efficiencies. Thermal efficiency. Any study of engines and power involves consideration of heat as the source of power. The heat produced by the burning of gasoline in the cylinders causes a rapid expansion of the gases in the cylinder. And this, in turn, moves the pistons and creates mechanical energy. It has long been known that mechanical work can be converted into heat, and that a given amount of heat contains the energy equivalent of a certain amount of mechanical work. Heat and work are theoretically interchangeable, and bear a fixed relation to each other. Heat can therefore be measured in work units. For example, foot-pounds, as well as in heat units. The British thermal unit, BTU, of heat is the quantity of heat required to raise the temperature of 1 pound of water by 1 degrees Fahrenheit. It is equivalent to 778 foot-pounds of mechanical work. A pound of petroleum fuel, when burned with enough air to consume it completely, gives up about 20,000 BTU, the equivalent of 15,560,000 foot-pounds of mechanical work. These quantities express the heat energy of the fuel in heat and work units, respectively. The ratio of useful work done by an engine to the heat energy of the fuel it uses, expressed in work or heat units, is called the thermal efficiency of the engine. If 2 similar engines use equal amounts of fuel, the engine that converts into work the greater part of the energy in the fuel, higher thermal efficiency, delivers the greater amount of power. Furthermore, the engine that has the higher thermal efficiency has less waste heat to dispose of to the valves, cylinders, pistons, and cooling system of the engine. A high thermal efficiency also means low specific fuel consumption and, therefore, less fuel for a flight of a given distance at a given power. Thus, the practical importance of a high thermal efficiency is threefold, and it constitutes one of the most desirable features in the performance of an aircraft engine. Of the total heat produced, 25 to 30% is utilized for power output. 15 to 20% is lost in cooling, heat radiated from cylinder head fins, 5 to 10% is lost in overcoming friction of moving parts, and 40 to 45% is lost through the exhaust. Anything that increases the heat content going into mechanical work on the piston, which reduces the friction and pumping losses, or which reduces the quantity of unburned fuel or the heat lost to the engine parts, increases the thermal efficiency. The portion of the total heat of combustion that is turned into mechanical work depends to a great extent upon the compression ratio. The compression ratio is the ratio of the piston displacement plus combustion chamber space to the combustion chamber space. As mentioned earlier, other things being equal, the higher the compression ratio is, the larger is the proportion of the heat energy of combustion turned into useful work at the crankshaft. On the other hand, increasing the compression ratio increases the cylinder head temperature. This is a limiting factor, because the extremely high temperature created by high compression ratios causes the material in the cylinder to deteriorate rapidly and the fuel to detonate instead of burning at a controlled rate. The thermal efficiency of an engine may be based on either bhp, or indicated horsepower, up, and is represented by the formula. Indicated thermal efficiency equals A times 33,000 weight of fuel burned / minutes, times heat value times 778. The formula for brake thermal efficiency is the same as shown above, except the value for bhp is inserted instead of the value for up. Example. An engine delivers 85 bhp for a period of 1 hour, and during that time consumes 50 pounds of fuel, assuming the fuel has a heat content of 18,800 BTU per pound. Find the thermal efficiency of the engine. 85 times 33,000 equals 2,805,000. 0.833 times 18,800 BTU times 778. 12,184,569. Brake thermal efficiency equals 0.23 or 23%. Reciprocating engines are only about 34% thermally efficient. That is, they transform only about 34% of the total heat potential of the burning fuel into mechanical. 1-35. Energy. The remainder of the heat is lost through the exhaust gases, the cooling system, and the friction within the engine. Thermal distribution in the reciprocating engine is illustrated in Figure 1-42. Mechanical efficiency. Mechanical efficiency is the ratio that shows how much of the power developed by the expanding gases in the cylinder is actually delivered to the output shaft. It is a comparison between the bhp and the A. It can be expressed by the formula. Mechanical efficiency equals bhp. Brake horsepower is the useful power delivered to the propeller shaft. Indicated horsepower is the total HP developed in the cylinders. The difference between the two is friction horsepower, FHP, the power lost in overcoming friction. The factor that has the greatest effect on mechanical efficiency is the friction within the engine itself. The friction between moving parts in an engine remains practically constant throughout an engine's speed range. Therefore, the mechanical efficiency of an engine is highest when the engine is running at the RPM at which maximum bhp is developed. Mechanical efficiency of the average aircraft reciprocating engine approaches 90%. Volumetric efficiency. Volumetric efficiency is a ratio expressed in terms of percentages. It is a comparison of the volume of fuel/air charge, corrected for temperature and pressure, inducted into the cylinders to the total piston displacement of the engine. Various factors cause departure from a 100% volumetric efficiency. The pistons of a naturally aspirated engine displace the same volume each time they travel from top center to bottom center of the cylinders. The amount of charge that fills this volume on the intake stroke depends on the existing pressure and temperature of the surrounding atmosphere. Therefore, to find the volumetric efficiency of an engine, standards for atmospheric pressure and temperature had to be established. The U.S. standard atmosphere was established in 1958 and provides the necessary pressure and temperature values to calculate volumetric efficiency. The standard sea level temperature is 59 degrees Fahrenheit, or 15 degrees Celsius. At this temperature, the pressure of 1 atmosphere is 14.69 pounds/2, and this pressure supports a column of mercury, Hg, 29.92 inches high, or 29.92 Hg. These standard sea level conditions determine a standard density, and if the engine draws in a volume of charge of this density exactly equal to its piston displacement, it is said to be operating at 100% volumetric efficiency. An engine drawing in less volume than this has a volumetric efficiency lower than 100%. An engine equipped with true supercharging, boost above 30.00 Hg, may have a volumetric efficiency greater than 100%. The equation for volumetric efficiency is volumetric, volume of charge, corrected for efficiency equals temperature and pressure, piston displacement. Many factors decrease volumetric efficiency, including part throttle operation, long intake pipes of small diameter, sharp bends in the induction system, carburetor air temperature too high, cylinder head temperature too high, incomplete scavenging, improper valve timing. Propulsive efficiency. A propeller is used with an engine to provide thrust. The engine supplies bhp through a rotating shaft, and the heat released by combustion, 40-45% is carried out with exhaust, 15-20% is removed by fins, 25-30% is converted into useful power, 5-10% is removed by the oil. Figure 1-42. Thermal distribution in an engine. 1-36. Propeller absorbs the bhp and converts it into thrust HP. In this conversion, some power is wasted, since the efficiency of any machine is the ratio of useful power output to the power input. Propulsive efficiency. In this case, propeller efficiency is the ratio of thrust HP to bhp. On the average, thrust HP constitutes approximately 80% of the bhp. The other 20% is lost in friction and slippage. Controlling the blade angle of the propeller is the best method of obtaining maximum propulsive efficiency for all conditions encountered in flight. During takeoff, when the aircraft is moving at low speeds, and when maximum power and thrust are required, a low propeller blade angle gives maximum thrust. For high-speed flying or diving, The blade angle is increased to obtain maximum thrust and efficiency. The constant speed propeller is used to give required thrust at maximum efficiency for all flight conditions. Gas turbine engines. Types and construction. In a reciprocating engine, the functions of intake, compression, combustion, and exhaust all take place in the same combustion chamber. Consequently, each must have exclusive occupancy of the chamber during its respective part of the combustion cycle. A significant feature of the gas turbine engine is that separate sections are devoted to each function, and all functions are performed simultaneously without interruption. A typical gas turbine engine consists of 1. An air inlet, 2. Compressor section, 3. Combustion section, 4. Turbine section, 5. Exhaust section, 6. Accessory section, and 7. The systems necessary for starting, lubrication, fuel supply, and auxiliary purposes, such as anti-icing, cooling, and pressurization. The major components of all gas turbine engines are basically the same. However, the nomenclature of the component parts of various engines currently in use varies slightly due to the difference in each manufacturer's terminology. These differences are reflected in the applicable maintenance manuals. One of the greatest single factors influencing the construction features of any gas turbine engine is the type of compressor or compressors for which the engine is designed. 4 types of gas turbine engines are used to propel and power aircraft. They are the turbofan, turboprop, turboshaft, and turbojet. The term turbojet was used to describe any gas turbine engine used in aircraft. As gas turbine technology evolved, these other engine types were developed to take the place of the pure turbojet engine. The turbojet engine has problems with noise and fuel consumption in the speed range that airliners fly. 8 Mach. Due to these problems, use of pure turbojet engines is very limited. So, almost all airliner-type aircraft use a turbofan engine. It was developed to turn a large fan or set of fans at the front of the engine, and produces about 80% of the thrust from the engine. This engine was quieter, and has better fuel consumption in this speed range. Turbofan engines have more than one shaft in the engine. Many are two-shaft engines. This means that there is a compressor and a turbine that drives it and another compressor and turbine that drives it. These two-shafted engines use 2 spools. A spool is a compressor and a shaft and turbines that driven that compressor. In a 2-spool engine, there is a high-pressure spool and a low-pressure spool. The low-pressure spool generally contains the fans and the turbine stages it takes to drive them. The high-pressure spool is the high-pressure compressor, shaft, and turbines. This spool makes up the core of the engine, and this is where the combustion section is located. The high-pressure spool is also referred to as the gas generator, because it contains the combustion section. Turbofan engines can be low bypass or high bypass. The amount of air that is bypassed around the core of the engine determines the bypass ratio. As can be seen in Figure 1-43, the air generally driven by the fan does not pass through the internal working core of the engine. The amount of airflow in pounds/seconds from the fan bypass to the core flow of the engine is the bypass ratio. Bypass ratio equals 100 pounds divided by seconds flow fan equals 5. 1 bypass ratio. 20 pounds/seconds flow core. Some low bypass turbofan engines are used in speed ranges above 0.8 Mach, military aircraft. These engines use augmenters or afterburners to increase thrust. By adding more fuel nozzles and a flame holder in the exhaust system, extra fuel can be sprayed and burned, which can give large increases in thrust for short amounts of time. The turboprop engine is a gas turbine engine that turns a propeller through a speed reduction gearbox. This type of engine is most efficient in the 300 to 400 miles per hour speed range, and can use shorter runways than other aircraft. Approximately 80 to 85% of the energy developed by the gas turbine engine is used to drive the propeller. The rest of the available energy exits the exhaust as thrust. By adding the horsepower developed by the engine shaft and the horsepower in the exiting thrust, the answer is equivalent shaft horsepower. 1-37. Figure 1-43. Turbofan engine with separate nozzles, fan and core. With regard to aircraft, the turboshaft engine is a gas turbine engine made to transfer horsepower to a shaft that turns a helicopter transmission, or is an onboard auxiliary power unit, APU. An APU is used on turbine-powered aircraft to provide electrical power, and bleed air on the ground and a backup generator in flight. Turboshaft engines can come in many different styles, shapes, and horsepower ranges. Air entrance. The air entrance is designed to conduct incoming air to the compressor with a minimum energy loss resulting from drag or ram pressure loss. That is, the flow of air into the compressor should be free of turbulence to achieve maximum operating efficiency. Proper inlet design contributes materially to aircraft performance by increasing the ratio of compressor discharge pressure to duct inlet pressure. This is also referred to as the compressor pressure ratio. This ratio is the outlet pressure divided by the inlet pressure. The amount of air passing through the engine is dependent upon 3 factors. 1. The compressor speed, RPM. 2. The forward speed of the aircraft. 3. The density of the ambient, surrounding, air. Turbine inlet type is dictated by the type of gas turbine engine. A high bypass turbofan engine inlet is completely different from a turboprop or turboshaft inlet. Large gas turbine-powered aircraft almost always have a turbofan engine. The inlet on this type of engine is bolted to the front, a flange, of the engine. These engines are mounted on the wings, or nacelles, on the aft fuselage, and a few are in the vertical fin. A typical turbofan inlet can be seen in Figure 1-44. Since on most modern turbofan engines the huge fan is the first part of the aircraft the incoming air comes into contact with, icing protection must be provided. This prevents chunks of ice from forming on the leading edge of the inlet, breaking loose, and damaging the fan. Warm air is bled from the engine's compressor, and is ducted through the inlet to prevent ice from forming. If inlet guide vanes are used to straighten the airflow, then they also have anti-icing air flowing through them. The inlet also contains some sound-producing materials that absorb the fan noise, and make the engine quieter. Figure 1-44. Typical turbofan inlet, 1-38. Turboprops and turboshafts can use an inlet screen to help filter out ice or debris from entering the engine. A deflector vane and a heated inlet lip are used to prevent ice or large chunks from entering the engine. On military aircraft, the divided entrance permits the use of very short ducts with a resultant small pressure drop through skin friction. Military aircraft can fly at speeds above Mach 1, but the airflow through the engine must always stay below Mach 1. Supersonic airflow in the engine would destroy the engine. By using convergent and divergent shaped ducts, the airflow is controlled and dropped to subsonic speeds before entering the engine. Supersonic inlets are used to slow the incoming engine air to less than Mach 1 before it enters the engine. Accessory section. The accessory section of the gas turbine engine has various functions. The primary function is to provide space for the mounting of accessories necessary for operation and control of the engine. Generally, it also includes accessories concerned with the aircraft, such as electric generators and hydraulic pumps. Secondary functions include acting as an oil reservoir, and oil sump and housing the accessory drive gears and reduction gears. The arrangement and driving of accessories has always been a major problem on gas turbine engines. Driven accessories on turbofans are usually mounted on the accessory gearbox, which is on the bottom of the engine. The location of the accessory gearbox varies somewhat, but most turboprops and turboshafts have the accessory cases mounted to the back section of the engine. The components of the accessory section of all gas turbine engines have essentially the same purpose, even though they often differ quite extensively in construction details and nomenclature. The basic elements of the accessory section are 1. The accessory case, which has machined mounting pads for the engine-driven accessories, and 2. The gear train, which is housed within the accessory case. The accessory case may be designed to act as an oil reservoir. If an oil tank is utilized, a sump is usually provided below the front bearing support for the drainage and scavenging of oil used to lubricate bearings and drive gears. The accessory case is also provided with adequate tubing or cord passages for spraying, lubricating oil on the gear train and supporting bearings. The gear train is driven by the engine high-pressure compressor through an accessory drive shaft, tower shaft, gear coupling, which splins with the gearbox gear, and the high-pressure compressor. The reduction gearing within the case provides suitable drive speeds for each engine accessory or component. Because the rotor operating RPM is so high, the accessory reduction gear ratios are relatively high. The accessory drives are supported by ball bearings assembled in the mounting pad bores of the accessory case. Figure 1-45. Figure 1-45. Typical turboprop accessory case. Compressor section. The compressor section of the gas turbine engine has many functions. Its primary function is to supply air in sufficient quantity to satisfy the requirements of the combustion burners. Specifically, to fulfill its purpose, the compressor must increase the pressure of the mass of air received from the air inlet duct, and then discharge it to the burners in the quantity and at the pressures required. A secondary function of the compressor is to supply bleed air for various purposes in the engine and aircraft. The bleed air is taken from any of the various pressure stages of the compressor. The exact location of the bleed ports is, of course, dependent on the pressure or temperature required for a particular job. The ports are small openings in the compressor case adjacent to the particular stage from which the air is to be bled. Thus, varying degrees of pressure are available simply by tapping into the appropriate stage. Air is often bled from the final or highest pressure stage since, at this point, pressure and air temperature are at a maximum. At times it may be necessary to cool this high-pressure air, if it is used for cabin pressurization or other purposes to which excess heat would be uncomfortable or detrimental. The air is sent through an air conditioning unit before it enters the cabin. 1-39. Bleed air is utilized in a wide variety of ways. Some of the current applications of bleed air are 1. Cabin pressurization, heating, and cooling. 2. De-icing and anti-icing equipment. 3. Pneumatic starting of engines. And 4. Auxiliary drive units. 2. Compressor types. The two principal types of compressors currently being used in gas turbine aircraft engines are centrifugal flow and axial flow. The centrifugal flow compressor achieves its purpose by picking up the entering air and accelerating it outwardly by centrifugal action. The axial flow compressor compresses air, while the air continues in its original direction of flow, thus avoiding the energy loss caused by turns. The components of each of these two types of compressor have their individual functions in the compression of air for the combustion section. A stage in the compressor is considered to be a rise in pressure. Centrifugal flow compressors. The centrifugal flow compressor consists of an impeller, rotor, a diffuser, stator, and a compressor manifold. Figure 1-46. Centrifugal compressors have a high pressure rise per stage that can be around 8. 1. Generally, centrifugal compressors are limited to 2 stages due to efficiency concerns. The 2 main functional elements are the impeller and the diffuser, although the diffuser is a separate unit and is placed inside and bolted to the manifold. The entire assembly, diffuser and manifold, is often referred to as the diffuser. For clarification during compressor familiarization, the units are treated individually. The impeller is usually made from forged aluminum alloy, heat-treated, machined, and smoothed for minimum flow restriction and turbulence. In most types, the impeller is fabricated from a single forging. This type impeller is shown in Figure 1-46. The impeller, whose function is to pick up and accelerate the air outwardly to the diffuser, may be either of 2 types, single entry or double entry. The principal differences between the 2 types of impellers are size and ducting arrangement. The double entry type has a smaller diameter, but is usually operated at a higher rotational speed to assure sufficient airflow. The single entry impeller, shown in Figure 1-47, permits convenient ducting directly to the impeller eye, inducer vanes, as opposed to the more complicated ducting necessary to reach the rear side of the double entry type. Although slightly more efficient in receiving air, the single entry impeller must be large in diameter to deliver the same quantity of air as the double entry type. This, of course, increases the overall diameter of the engine. Figure 1-47. Single entry impeller. Included in the ducting for double entry compressor engines is the plenum chamber. This chamber is necessary for a double entry compressor, because the air must enter the impeller diffuser compressor manifold. Air outlet elbow with turning vanes for reducing air pressure losses. Figure 1-46. A components of a centrifugal flow compressor. Air outlet elbow with turning vanes for reducing air pressure losses. 1-40. Engine at almost right angles to the